I started the recording and I'll paste the link in the chat where I'll be taking some notes, but everyone feel free to take some notes as well. And as you can see, I've already populated some info there and we'll have the formal agenda starting now. I send that through email. So you might expect similar formats for future working groups where I'll send you a calendar invite, follow up with an agenda, and we'll be working off of that. I think in this case, yes, we will make the recording available as there is a lot of technical information that Tamas and Billy are going to introduce ourselves. For future meetings, we can see depending on how much practical material versus theoretical material. But I can send this recording via email. And so with that, Tamas, feel free to get started.
Okay, do you guys see my slide properly, and can you hear me?
Yes.
Let's see if it advances. Okay. So, hi everyone again, and so in this first working group meeting, we wanted to provide kind of a general overview of how we collect this CT data and what are the data types, and some details of the analysis that we perform. So the first part will be presented by me, kind of a general, and some knowledge about other software tools. And then Billy will take over and get into the details of the ISO-based porosity analysis. Hope it sounds good. So my agenda is to provide a brief overview or intro into X-ray computed tomography, or XCT, then talk a bit about the MONet-specific XCT workflow, what are the data types, and then some other optional output formats and some software tools that can be used to view or analyze the data. So what is XCT? It is a non-destructive X-ray imaging method that can reveal the internal microstructure of objects. The output of CT is a series of radiographs as raw data, which then is reconstructed into a 3D volume data on the computer. So hence the name computed tomography. And in the CT images, the components are differentiated in the image data based on their density, specifically electron density, which is related to their X-ray absorption. Heavier elements with more electrons absorb more X-rays. And since this is a transmission technique, we detect the X-rays that are not absorbed, that went through the material. And so the difference in the X-ray absorption results in different intensity on the detector and in different gray scale intensities in the images. This is our CT, an image of a EMSL CT system with a MONet core inside. It's kind of a large cabinet system and easily house the MONet cores. Below it, Anil, our former colleague, is posing proudly with one of the MONet cores. So in this scanning, you can see the schematic on the right. We put the core on a turntable, a rotating platform, and the X-ray source is kind of a point source. So like a flashlight, there's a cone of light that goes towards the sample. And so that shows you that in order to capture a certain size or height sample, you can move it closer or further from the source. And that also determines your spatial resolution. And so during the scanning, the sample takes a full rotation, 360 degrees. And at small angular steps, we record these radiographs or X-ray images on the detector, about a couple thousands of them. Or for the high resolution data, we actually collect more than 3,000 per scan. And because, so I mentioned the density, electron density, the detector and the the geometry of the measurement enables the computer to basically know that each voxel, which I will define later, each voxel that is detected in the image has the XYZ coordinate of that location and the related X-ray absorption intensity. So that's how you can relate back to the 3D image and know where that component is in the data. So I want to define a few key terms. Voxels is just like in photography, the 2D pixels. Here we talk cubic pixels called voxels, and the size of them basically determines the spatial resolution, sometimes called voxel resolution. But I also want to note that by rule of thumb, in the CT world, we kind of define the actual spatial resolution as double the voxel size. And that's one reason is that typically you need more than one voxel to see what that feature is. And then the 3D data can be viewed as slices. You can imagine slices cut or basically, slices building up the whole object with voxel distance apart. And those slices can be taken in any of the axis directions. And the sum of the slices is basically an image stack that builds up the 3D data. And then segmentation is the process of feature extraction. The MONet core is shown as an example where we segment the porosity, and then we can visualize it in 3D. Grayscale versus RGB. So grayscale is the raw data. As I mentioned, that different grayscale intensity corresponds to the different absorption. It's basically a grayscale image has one intensity value for each voxel, while a colored RGB image has three values associated with each voxel: red, green, and blue intensity. And mesh is often used to simply represent 3D data by basically connected triangles, and that can build up a 3D data. It's called the mesh. And a radiograph I mentioned is basically the X-ray image that is inverted in color after reconstruction. So the lowest density part, in this case air, would be black, and the highest density would be white, and everything in between. So in MONet, we have, as you guys know, we have a lot of cores we analyze, and so one workflow is the one that contains the chemical analysis. But I want to just point out the second one, which is the abiotic cores go to the CT. So that's framed there, where we collect lower and higher resolution scans on each core, 4 scans total. And then after that, the cores get subsampled for the hydraulic property measurements. And these scans, so I mentioned the low resolution scan is 2 scans at 82.5 microns voxel resolution. These are collected so that there is overlap between the 2 tiles so that we can merge the 2 scans into one single data set. And so to get a full image of the core. And then we collect higher resolution scans from the top and bottom half of each core at 38.2 micron voxel resolution. That's a compromise. It would took about 5 scans to get this high resolution data on a full core. So we settled with 2 quicker scans and 2 long scans to get the porosity specific data. So that's done on the high resolution data. So again, the whole core scan, this is an example of a merged data in the image. So it gives you a nice picture of the soil horizons, the heterogeneity of the soil. And this is not high enough resolution to do full pore network characterization. And that's why we collect the other 2 data sets. So here the spatial resolution is estimated to be about 165 microns. And I'm listing the scan conditions here. it's fewer projections than the high resolution scan, and the shorter exposure time. So that allows us to collect shorter scans. And this image here at the bottom is just from my computer. It's not, may not be very informative, but it's meant to show that for the lower resolution, the top and bottom scans, in the reconstruction folder, you can only find these two files. One is top is the VGI file, which is not shown here, the extension. And the other one is the more than 10 gigabyte size volume file, which is the actual data. But there's no other so segmentation or other data here for the low resolution scans. And then for the high resolution scans, where we collect one from top half and one from the bottom half, these are collected at the maximum projection number, 3142, and a longer exposure time to get better quality images. Here, the resolution is about 76 micron, and that allows us to detect enough porosity to visualize those pore connectivities and capture most of the porosity. Obviously, nothing is seen under the 76 micron size as pores, so there's this limitation. In the downloaded data, you would see a segmentation folder in addition to the raw data, the VGI and the volume file. And in that segmentation folder here, I'm showing kind of all the files that are there, Aviso project files, the spreadsheet with the porosity data, and the individual images that are basically snapshots for you to see the porosity. We have to reconstruct the data before analyzing it, and we do that using the scanner's software. It's called the Metris Suite. CT Pro 3D is the software, and it's basically goes through this iterative step of finding the center rotation, and then so basically get a focus reconstruction as shown on the right, just one slice there, top view. This is about a 20-30 minute process to get the reconstruction done manually or semi-manually. And then this is that Billy will talk about in the next talk. Here I'm just showing that on the high resolution scan, as you can see on the right, we do this detailed pore network analysis, identical analysis for the top and bottom half, providing the porosity metrics, and then also performing pore network analysis for pore connectivity and image-based estimation of flow and transport properties. And then just to summarize what's in those folders, so the image data, we have for the lower resolution scans, we have a merged data set, merged image data, and then for the higher resolution scans, we have, of course, the raw grayscale data, and then those porosity images saved as individual images as well. And now this year we started basically saving off from the Aviso segmentation the segmented porosity data, which is basically a binary data, pores and everything else, and we create binary image stacks for each of the connected, unconnected, and all the pores, because we figured that would be a useful thing to also visualize for the users. And then these are the numerical data that Billy will talk about in detail: pore size, pore volume fraction, connectivity, bulk density, permeability, flow rate, and tortuosity that we can all define for you as well. And then for the bulk density, that's obviously it's an estimation based on the images using the Hounsfield units, which is the grayscale intensity basically. And so there's a way to estimate based on the absorption coefficient. In this case, it's just basically a grayscale value for a voxel that is of the soil and for the water field pores. And using that reference, we use this formula embedded in a VISO to estimate the wet bulk density of the cores. And we found it to be a reasonable agreement in the physically measured bulk density. And then these are the data processing steps that Billy will talk about in detail, how to basically read in the data into a VISO, initial cropping, and then do the segmentation and get the outputs that we put out. So now I just want to talk a little bit about some things that might help you to know how to open the data and view it and what to do with it. So in addition to what we provide for MONet, we can also create animations like this from the data for publications, convert the segmented porosity into a mesh or an STL file, that is a stereolithographic file that can be 3D printed, or just opened for easy visualization. I'll show you how. And for numerical data, we can also calculate pore throats, pore coordination numbers, and just as Billy and Sharon mentioned, as she requested, numerical spreadsheets for only the connected pores that can also be done separately. So recognizing that not everyone has a VISO, that's the program that we use for analysis, and it's an expensive licensed software that also has a learning curve. I just wanted to mention that the volume data as well as the image stacks can be opened in free software such as ImageJ and Fiji. And so for that, I have to note though that just running the high resolution data is 30 gigabytes, so it may not be easy to open it on a laptop. So we actually use kind of high-end desktop computers in our CT lab that can handle that 20-30 gigabyte data sets. But even though it can be opened in ImageJ, it may not work or maybe crash on your laptop. So that's the issue of just a large data size from CT. But I recommend this ImageJ, Fiji ImageJ package with batteries included because it has more features. And I downloaded a 64-bit Windows version on my computer. And then, so that's just an installation note that you can just install it on your C drive and run the application executable and create a desktop shortcut for it. So this is how you can open the .wall file. I'm showing here on the top left, kind of the reconstruction folder for a high resolution scan, because you can tell it also has a segmentation folder. So the volume file you see is 31.25 gigabytes. So it's a huge file, but it can be opened in ImageJ. You have to open the VGI file that is above it, and that's what I'm showing here at the bottom. The VGI file is opened in a text editor in Notepad, because you can read from the VGI file the size of the images. This is 2000 by 2000 by 2000 pixels, basically using the full detector image. Because that number, when you open ImageJ and say a file import raw, like shown here, the window, you have to select for the volume file 32-bit real, and then enter just 2000 by 2000 by 2000, leave the offset 0, and then make sure this leave the NDN byte order text box is checked, or a checkbox is checked, and then click OK. And after a few minutes, your data set will be opened, and it looks, you see, it's like 30 gigabytes. And you can slice through it. You can see this kind of progress bar at the bottom. You can scroll through the whole image and able to see it. I would recommend to, if it opens on your computer, to go to image and type and convert it to 8-bit, because it will be much smaller and still useful. And then, well, just a few tricks that you can adjust the image contrast by going to image type. So image, adjust, brightness and contrast, and just using the auto setting, applying it to all the slices will give you this kind of enhanced contrast. You can see, for example, the high density mineral components in white, and also the pores in the background, so outside there and inside the object, the soil core. And then filtering often can help kind of meet with this heterogeneities in the intensity. Like here's a pore, and it seems like there's gray area in there, which can be real resolved organic matter or water fields, but it's really pore. So maybe with filtering, you can make it as a single phase, and makes your segmentation easier. So for that, I would recommend process filters, median 3D filter with a kernel size, which is just the number of voxels it applies to, kernel size 2, and then it will get you a bit more homogeneous image for each phase, and maybe help with the edges for the segmentation. And what is easier to open on your laptop is the binary image stack. I mentioned that now we are started to include the segmented porosity. And so for older projects, you have to request it, and we'll go back and create them. But these additional folders would show up in the segmentation folder, where you can see a binary stack for all pores, connected, unconnected pores. And these can be opened as an image stack or image sequence. So in ImageJ, you go to File, Import or Open Image Sequence, and just within that folder, selecting the first image and clicking OK will open all this, in this case, 1500 or 1600 slices. And if we look like this, it's a binary image where the pores are white and everything else is just zero or other. And so this data set can be used to visualize the pores only. Here I'm showing an ImageJ example where we can also, so it's still sizable. This image would be still 2.2 gigabytes. You can create a STL file of it using ImageJ, which will be much smaller, and I'll show you an example. But basically, you're doing that using the plugin available in ImageJ called BoneJ, and you have to use the isosurface component. This window will open up. I just leave the options as default, resampling threshold at the default values. This is checked show surface by default. And then after clicking OK here, an ImageJ 3D viewer will open up, and this on the small window, but no other thing. You just have to wait for this window to open up. Well, you go to File and scroll down, Export Surfaces, and select STL binary. We will have these slides for reference, so you can check this out and do it yourself. But STL binary basically will create this, and I just save it in the respective folder. In this case, I named it Connected Pores STL. It will just show up, and it's just a 43 megabyte data as opposed to 2.2 gigabytes. And then that STL can be used for 3D printing. An easy way to view it is this free STL viewer. This is the link, viewstl.com, where you can just drag and drop your STL file, and you will, once it loads, you will see the 3D image that you can interact with. You can rotate it around and view that. And I have this live example I can show you in a minute. So here are a slide with the different software tools, Aviso at the top, and the ImageJ I mentioned, and we listed some other tools, such as also ParaView is a free tool, OpenPNM for pore network modeling, PoreSpy, pFlowTran, OpenFOAM, for different analysis and simulation types, such as computational fluid dynamics, for example, OpenFOAM. And here are other software that I already mentioned, the OpenPNM and PoreSpy on the previous slide, but there are other 3D visualization tools like Aviso. One would be VG Studio, Visual Graphics Studio, and Dragonfly. Those all need to be purchased, although most vendors allow either to download a demo version or a trial period to check those out. And then the others are I mentioned. So okay, before moving on, I like to show you a quick demo of the opening an STL file. Just share another screen. So can you guys see this screen where is the view STL open? I just want to grab source file here and show you. So this is online, and you can basically so this you can generate from the image stack that we now save of the binary image stack for the pores.
Thomas, we're not seeing your screen. I don't know if
I'm sorry.
you are okay.
How about
There
now?
you go.
Okay.
It's loading. Okay, now, yes, you might wanna go back and like repeat because we are not seeing.
I didn't notice that it didn't take the share check click. So this is the view STL that I showed you before, and so you can just grab your STL file that you created into this tool, and you get basically a 3D visualization of the porosity. So this you can get from the image stack that we save for the pores now, the binary stack, and convert an STL into an STL, and then you can open it with this STL viewer. Okay, so just want to close up here with the end of the presentation. So I'd like to thank the MONet team and because the OEB are from the funding. These are not all the folks, but I couldn't get everyone here real quick. And then I wanted to see if you have any immediate questions, quick questions to this part before we move on to Billy. We can also entertain questions in the end, but if you have something immediate, I'm happy to answer.
I have one question, Thomas, for the scanning. Were the cores scanned with the in situ water content, or were they dried before they were scanned?
They are scanned as received.
Okay,
so the pore is inundated and wet, then it should be in the pores.
Okay. So you have water, air, and solid phases that you can distinguish.
Yes, and for the purpose of these segmentations, the pores are basically air and water, and potentially some root material as well. So we don't separate them, and we're not able to even. We don't have kind of the image contrast to separate air and water in this at this resolution.
Oh, you cannot. You cannot.
So it's basically in the scale, it's one phase.
Okay, so basically you don't have the distribution of the water. You just have the pores.
Right. Yeah, containing the water or an air.
Yeah. Okay. Thank you.
So now I will hand it off to Billy, who has some really cool images and all the details about these data types and how we get them in Aviso. So Billy.
Thank you, Tomas. Okay, so let me share my screen here. Here we go. Okay, come on. All right, can everybody see what's going on? See my slides?
Yeah.
Okay, good.
Looks good.
All right, good. So Billy Peterson, once again, post back here, working under MONet. Went ahead and put this together on the Aviso analysis on what we do and how we get it going. Tomas covered a lot of the, in depth, more in the weeds. Mine's going to be more of a how-to. Real quick, you can say it in the chat or not if you want or whatever. Who's used Aviso before? You got any, any experience with it? It's a complicated program. So let me see here. Oops, wrong one. Oh, I'm doing a great job here. Okay. Oh, there we go. All righty, moving right along. There we go. Okay, so MONet data types. We're going to go start with our images. So first of all, we have a whole core here. This is just one we extracted from the double scans that Tomas does, just a top and a bottom. Moving from there, we have our raw images, which is the area that we analyze, which basically the reason it's a square and not just doing the entire core is, as you all know, with the kits, it's a core that goes down and it's going to disturb everything around the side. So we just take a like sample from the middle and it's the same on every one. So all the data, it's going to be standardized. From there, we extract our pores. From there, we get our connected pores. We also get unconnected pores, which is pretty simple. It's just core is a function where you say pores minus connected pores equals unconnected pores. And then finally, the one that gives you a lot of data, the pore network model. Now moving on, we're going to go into the raw, which is basically, like I said, it's a fresh, unaltered scan in grayscale. And as you can see here, as she's going around, you can see the divots in there, the cracks, even the rocks. So this is the voxels that we crop to every time, and every sample that you see coming from us is going to be universal.
May I ask a question, Billy?
Yes, sir.
Okay. When you say connected, non-connected pores, does that mean that the connection is dependent on the resolution, right?
Let me go back here real quick. The connection itself, actually, let's go to the next one. There we go. The connection itself is actually based on the voxel and the voxel location. So if we have voxel here, and it does a measurement of all of them around it, there we go. Does a measurement of all of them around it, and then it does a measurement of that one, which is connected, then that one, and then that one. So, and it's based on connectivity from the maximum to the minimum points of the pore. And it goes in all axes, all three axes. So you're getting, when I say connected pores, you're getting, something that is connected one way or another all the way down. And in my little demo, my little video, I'll actually show you what what Aviso actually classifies as a pore, because this unfortunately, this one that you're seeing right here on the screen is not the one I use in my video. It's got a lot of pores, but it actually has some really big spaces. And based on the geometry, it actually has a really kind of a cool way that it actually isolates segments and classifies a core. And it does it with very easy to see colors, if that's necessarily what you're after. But yeah, we can I'll show you that here when we get to it. Did that answer your question at least?
Yeah, not quite. So because the resolution is 38 micron per voxel, so could there be pores? Because pores that are smaller than that you couldn't detect, right? So
yes, sir. Oh, sorry to interrupt. Go ahead.
So you wouldn't know whether there are smaller pores that are connected, right?
So usually, generally, after we calculate flow rates, I mean, and yes, basically, yeah, if it's below our intensity or our scan range, then obviously we can't get it. And we actually get a warning every time we run Aviso. We get a warning for this, unable to detect this many pores, but it's like 1%. I'm unable to detect like 1% of pores because they're so small. So
thank you.
No problem. If anybody else, if any questions, feel free to interrupt and come on in. Let me know. Got no problem answering them. You're shifting gears here between different subjects. It's easier to stay on that topic. So,
Billy,
Mr. Flurry, that was great. Yes.
Billy, this is Sharon. I have a question. So,
yes.
So is it 1% of pore volume or 1% of the number of pores?
1% of the number of pores.
Okay, thank you.
Yeah, no problem. And yeah, going over what I just did for your cores is actually related to that because it's actually using for connected pores. So not on overall pores, but just connected pores. So. Alrighty, this is, once again, it's pretty simple. It's the size and the shape, and based on that is what Aviso does the analyses on. So to us, it looks like, you know, a blob on the screen with some hair coming off of it. But in Aviso, it's measuring voxel size and converting it. So we're getting an actual really good measurement of the pores themselves. Further analysis. Now, okay, then we have, oh, I'm sorry, this is connected pores. The last one's regular pores. Versus the last one, let me go back. So we have all pores, connected pores. So this, Mr. Fleury, this is the same way where it isolates from, you have from the top to the bottom, as you can see. So it isolates what's connected by axes, and we do all three. Okay, and yeah, once again, based on axis. Size, we do, once again, size and shape analysis on all of these. And we also use this data in particular to calculate flow rates. And then once again, we have the unconnected pores, which is basically what it sounds like. There's no connectivity. I call them islands because they're just kind of floating out there on their own. So some people call it noise. Okay, and this is the generated pore network model. This is a computer generated image, obviously. Pull something up here. And it is based on, oops, pushed the wrong thing. It's based on volume, equatorial radius, and channel length. And it's kind of interesting because we can actually get a spreadsheet with this, associated with this, that actually gives us like X, Y, and Z location, so you know exactly where those pores are. Also gives us the individual flow rate of that pore. So that's also something we can extract. Okay, moving on, we're going to the image thresholding, how it's done. Now this GIF file that I have on here, you can see I'm starting from low to high, rocks being the highest. And then we're going to go back from high to low. So you can see kind of how it works. It's kind of a sliding bar you use. You just kind of do it by hand. You just kind of got to use your best judgment, but there is pretty much some rules of thumb you got to follow. So, and by doing this off of the grayscale values, this is basically how we create our binary object. Now, this is kind of cool, this little slide here, because what this is telling us is giving us an idea of kind of how it classifies a pore. So like you're gonna see this right here is an example, great example. And it's going to say, okay, here's a pore, now here's a pore, here's a pore, here's a pore, based on the geometry, the shape, and the rate that the voxels change. So with those grayscale values is actually what it's doing with its statistical stuff, is telling you, you know, we believe, you know, right here it's going like this. So it will base on the rate of change. All righty. And thresholding our pore spaces, and this is an example of doing it from minimum to maximum. So you see pores and no pores. Yeah. So you kind of go a little over each time, and it kind of gives you a kind of that rate that you get between, you know, black and white. It kind of, to go over a little bit is actually a good thing, because it's making a determination, but it's better to err on the side of more pores. And this right here is done by hand by a human, obviously, but right now we're looking into automating. And this part right here is that Thermo Fisher has a deeper learning, which is an AI tool. And we're trying to get that going after we're done, you know, trying to script the rest of it, which we're almost done. Alrighty. So this is the blending, or let's see, hold on a second. Minimize my stuff here. I get a little lost. Okay. Okay, yeah. So reasoning, it like I just said, it goes over a gradient based on the rate and the weight of the image, if you will. Why is this thing not going? And here's an example. Just these aren't real numbers. This is an example of, you know, we have nothing, 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 and then all of a sudden soil or matter or mass. Whereas it creates a gradient based on the confidence level of what it believes it should be there. Alrighty, and this is kind of a cool thing I did here to give you kind of an idea of how that is done. So you see, like here we have this area here versus like this area here. So this might be two objects that are different, but at the same time, you're looking at the rate in which these go down in their intensity level and then come back up. It actually, the computer actually makes a determination that, yeah, I think these are connected versus like right here, which we might say, hey, there's probably something there light, but the computer will make the determination based on your thresholding. It's a pore. So getting on to our numerical data, this is pretty straightforward. We have our scan information up top, pore sizes generally off to the side over here. This is a summarization of all of the pores and a summary of them all. Now we can get individual data. Coming onto this project, I didn't know Excel had a bottom. Apparently it's 600,000. Yeah. So these get in the millions generally. Fun side note, Cheryl, if you're still with us, when I did yours, it was about 3,000. So the connected pores was about 3,000 versus several million, which I just found fascinating. Somebody who stares at this all day. Let me see, our volume fraction. So in this case, this times 100, you get 34%, 34.7915%. Our pores, our pore connectivity, we have two here. This is the raw number that we get, but then we divide this by this, and we would get 98.17 percent of connected pores. From there, we get our estimated wet bulk density, which is based on the equation that Tomas posted earlier from Tanaka et al. This right here is based on the adding water calculation to the grayscale value. And then from here, we get our permeability, flow rates, and tortuosity, which is, yeah. And that would conclude that. Now, excuse me one second, pull this up. Now, I created a demo video here of the process. It takes me 4 hours to do one analysis on one core. I went through and I cut out all the waiting time, and it equals a 17-minute video of actual labor. So playing it on ×2 speed even, so as not to keep this going all day, and I'll give you kind of a narration of what's going on. So when we open a VISO here, this is basically what we first see. It gives you your vol file, ortho slice, and then this generally starts right in the middle of what you got. So let me speed ×2. If this goes a little fast, please let me know if this is going too fast for you. I'm just going to kind of give a just kind of a quick narrative with it. So starting out here, move our things around. As you can see, this is a slice. We can go through the slices. Adjust it to histogram so we get a better view. And see, as I pull the bar back and forth, I'm going through the slices. Now we do have to crop the top and or bottom off of every pore due to the fact that when you get the scan, you get like an anti-cone shape up top. So we have to take that off or it'll read it as a pore. So we adjust for that on every single one. They say it's weird hearing yourself on a microphone. It's even weirder watching yourself work, in my opinion. Okay, after we get that, this is where we get into our thresholding. Adjust that to histogram. This is where we convert it to a binary image. Go a little under. Okay, here we can see with this one, there's a lot of roots and a lot of pores in this one. This is one of our neon cores, by the way. And you can see I take it over to the high to low, just to kind of show. So with generally what we do is we cut out organic matter, most organic matter, and air and stuff like that. So one of the things we can do, and we've done this, we do this with other projects, we can do like root analysis. We can give you maps of the roots that are in there. We can give you maps of higher density versus lower density and pores. There's a lot of different, the possibilities are endless. With this, we're going to rename it pores because we'll forget, or at least I will. Here's where we visualize the data. All right, let's see. Here we're going to measure the data. We're going to measure the binary image size, voxel size, versus the actual scan data that's there. Gives us this, which in this case is 34.7915 times 100, 34.7915%. Also here, we have the data visualized. We can move it around, take a look at it. This is kind of neat. I zoomed in here so you can see exactly what it's looking like up close. Your little voxels. All right, this is where we analyze the pores. With this part right here is a preset we do for porosity. Now under these presets right here, you'll see it's volume, area, equal diameter, and area fraction. There are a lot of different things we can add to this. We can do different types of geometry, shapes, everything. And if you're not dealing with a binary image, you've got a lot more to deal with. But afterwards, and that would have taken 5 minutes, by the way. Afterwards, you get this. Yeah, lots of data, individual pores. This is where we scan it for connected axes. Oh, here we go. This is a visualization of what it classifies as a pore in this case. So you've got that big clump right there, and then everything else that you see down there is generally its own thing. Now we're going to do connected. This will actually do the scan from top to bottom, left to right, based on the axis you select. And if we see here, this is what the connected pores in this look like versus unconnected, or versus everything. Once again, connected. From here, we're going to measure the fraction of that, what percentage of that is, of the connected pores there is, and that's where we get that equation, or for the division we do earlier on the earlier we did on the spreadsheet. And here's where we subtract regular pores from connected pores, or connected pores from regular pores, and we get this, which is our unconnected pores, which you can see is just islands or noise. Reminds me of TV static from the 80s. Now you can't unsee it. And then here, from here, okay, so this part right here, separate objects, takes 30 minutes to load. You get it in 3 seconds. You're welcome. So we're checking connected objects by axes, and we're having it classify them as individual pores itself. Now this is really cool. Then, Sharon, this is what I had to go in and redo right here, and then do the label analysis for yours. I learned something from this, so once again, thank you. And we get this, individual classified connected pores. So from there is where we can do our calculation for our flow rates. These take 30 minutes apiece. And here we have our input and output pressures, which is based on an equation that was given to me for water itself. And there we go, 1.4, they're smaller, with Mr. Fleury, as we were talking about. And here's where we get our flow rate, permeability, tortuosity. And we do that for each axis. Okay, from here, we're gonna start our analysis on the solid material. So we threshold the solid material, which is basically minimum and maximum of the thresholding that the scan already did, which is easy, boom, done. From there, we apply arithmetic to the entire core. Well, we apply arithmetic, I should say. Somebody's trying to message me. So this is the equation from Tanaka et al., which is assigned for this core. We have the results, and from the results, we analyze that based on our binary image. And this is a lot like the label analysis where you can pick a lot of different scans. We just use the mean. We just want the mean. Gray image, apply, solid analysis, got it right over there on the right side. That gives us the mean, and that's about standard. You get between like 1.3 to 2.3. And then for visualization, I got to apologize. I forgot to do the network area or the network model, but I get to it at the end. And then from here, we do our screenshots and exporting our data. And then I go in and I grab all the data and throw it in a spreadsheet. Okay, and here's a poor network model. So there you go. It's good visualization of the flow rates. Here's the data that's collected as we went over in the first slides. And then once again, our output data that we got, Tomas went over this. It's basically the output data as I get it before we make the binary stacks. And that is it for that. Alrighty. What's this share screen thing? Let's see, did it stop sharing? Oh no, it didn't stop sharing. You see my awesome background. There we go. And that's it. Is there any questions?
Billy, there were some questions in the chat, but I think Tomas answered them there. So if other people have other questions or comments and that they would like to discuss now.
Let me see. Yeah, Tomas answered that. Let's see how XCT data different from BN roots. Yeah, as Tomas answered with this, for the let's see. So you can actually do it to detect between error. I'm sorry, let me move my thing here for ergonomics. You can actually use XCT in this form, like this, to be able to detect roots and other things like that. It's just based on a solid matter thing, or you looking for the solid matter, and you just got to kind of find that right threshold. One of the things that they were so nice to provide me with here for doing roots is a really cool drawing tablet, which you obviously can't see, and a lot of it involves a lot of writing and a lot of coloring. So there is something valuable I got from kindergarten. Let's put it that way. Lots of coloring. So you have to go through each individual slice and you have to like basically follow a route down, and you can tell when it's a route. Like you've got an actual thing going like this and then branching off. You just got to kind of follow it down and just mark it in there individually. And then there's other things we can use for when we do stuff like roots or anything special like that, that have little algorithms that can actually help detect them, that are, even if they're not a connected pore, you can actually use them that'll actually help detect what that area is, as well as if it's looking a little rough and there's too much other kinds of organic matter out there, you can actually erode away a certain amount of layers. If you saw the voxels when we zoomed in, you can actually erode away a little bit of those or a lot of those. There's a lot of different tools that we have at our disposal. And I've compared it this way before when I was first learning this stuff, is it's like you walk into a garage to fix a car and there's a wall of tools and every single one of them has a specific function. And you're like, I just need a new spark plug. So that's kind of what it's like. So see numerical table porosity, numerical table porosity. Yes. Now, the numerical table that I provided, that one there, for example, that was in the slideshow and the presentation, was on generally all the pores, like kind of all together. And I keep going back to Cheryl, who's not here now, unfortunately. She actually reached out to us, said, "Can you get me that on just the connected pores?" And it wasn't a big deal. I actually figured out how to do it and was able to provide it. So we don't on the connected pores. They are in there, but if you want specific connected pores, it is possible to do. Odetta?
Yeah, I actually wanted to follow up on the question that Carl asked and other people. Thomas, currently, are we providing the information on the routes or not on MONet course?
No, we are not.
Okay.
Yeah, generally this is the standard methodology that we're using for MONet, so it's kind of just flat across the board. Other XCT projects, though, it is an option that we can do that, or we can look into whatever else needs to be done. I will say also today, hearing a lot of what you guys are looking at, and I'm on the MONet team, but I'm usually busy, so I don't get to get in on all the calls, the kickoff calls. But it's really encouraging to hear what you guys are working on and to be a part of that, to be able to provide you guys information. I think this is really awesome. And when I believe it was Bradley, I think you were talking about you're doing root, or you're looking at, it was a root thing. I can't remember what. But I was thinking about this as you were talking. I was like, oh yeah, we could do that. So, is there any other questions? Oh, that's what I meant. Vegetation changes along the gradient. I was thinking about that. I was like, well, we with XCT you can look at the roots and you can actually get a map of them. So, and then volume and area.
Ideally, we would need to do more targeted scans on
Yes.
For good route segmentation, and so it's not part of the standardized workflow at this point. But if a MONet user like you reach out that, hey, what can we see, then we might be able to do some more.
So the only drawback with doing roots is that or any underground biomass, is that you're going to run into the issue of stuff that's not connected, or roots that like get less dense in an area, and the sorting algorithm will go over it and be like, oh, there's nothing here. So you have a root going nothing and then starting down here again. So that's where humans have to come in and go, okay, right there. So they take a lot of time, but you get some really cool stuff out of it. You get really cool images, you get surface area, you get, everything else. Is there any other questions? All right, Vanessa?
Yeah, so if there are no other questions, then we can hop off a little early. So after this, I'll check the recording and make sure I have a way that I can share it efficiently with everyone, either through a YouTube link or something else. So that might take a little bit to be available, just depending on how I can share it. But either way, I'll be following up with an email with some of these resources and the links to that we put in the chat, and I will converse more with the team and let you guys know what we will be covering on future meetings soon, as well as the dates for those. Probably the next one will be sometime in the next month, but yeah, you can expect similar time of the day, just maybe a different day, and in next month. Yeah, Tamas, go ahead.
Yeah, I just wondered about that what is your plan to gather that kind of feedback from this group in order to figure out what best to cover?
Yeah, so I can try to send out in the email that with all of the links a little bit of a survey for you guys to detail if you have thoughts on what you would like to cover on the next meeting. And you know, if not, we can do our best, but obviously it's better if we have your thoughts so we can prepare with what you want to hear from us. But yeah, probably I'll send out a Google Forms or something like that to collect some thoughts on how else you want this series to continue.
Yeah, and we can include related staff who can talk about that kind of modeling or simulation or use. Yeah, sorry, Odetta.
Yeah,
Yeah.
Odetta?
I was just wanting to add for everybody that is here for the first time is that this working groups is a very new approach from us, and it's the second working group that we have launched. From the previous working group, we found out that some of the participants were interested to have a scientific objective and just explore that, you know, with questions about, you know, the data that could be addressed by taking a more broader approach on all the sample analysis that have been completed. So please let us know what you'd like to get out of this working group. We have 2 more, and then we move into the office hours. So just reach out, let us know. We'd be happy to accommodate, and we also know how to shape them better in the future. And we understand that every working group might be different based on different type of different type of data that we are covering. So yeah, give us feedback. We'd love to hear from you. Thank you.